Hello. All right, so here we are beginning Module 13. Okay, so we are looking at exponential growth and decay functions. So we've talked a little recently about exponential functions and particularly geometric series and sequences. So a geometric sequence is where we have a sequence of numbers, and to get from one to the next, we multiply by something. So if we were to graph that, as you go from small x's to large x's, you would, if your value that you're multiplying by every time is a number larger than 1, it'll curve up, right? That would be a growth function. So we're going to talk more about that here and kind of explore exponential growth and decay functions and figure out how we can pull information out of them. So our objectives today are to graph exponential growth and decay functions, and to evaluate exponential growth and decay functions using a graphing calculator. So I'll be showing you some things later on my TI-83 Plus. Those of you who have a different model, it should be similar, and if you don't have one, you can use mine. Okay, so but we're looking again at graphing exponential growth and decay functions and evaluate them on a graphing calculator. So first of all, and I know we haven't done many YouTube videos in this class. If you need to, you can zoom in on YouTube to see what's on the board. I know sometimes it's kind of hard to tell. Okay, but I have a general growth function here and a decay function here, and our exponential functions are such. Or we know that they are exponential functions when we have something in the form of b to the x. So when the exponent x is, or when the variable x is in the exponent, we know we have an exponential function. Okay, so whereas like a parabola is characterized by x squared, that's a quadratic function. If there's an x cubed, that's a cubic function. If we have some number to the x where x is in the exponent, then we have an exponential function. Okay, so an exponential function, an exponential growth function, shoots up as x gets larger, and that's when b, the number being raised to the x power, is greater than 1. Okay, so think about this. The b is the number I'm multiplying by each time, right? So as x is 1, I just have my b. As x is 2, it's b squared, so I've multiplied by b to get to the next value. When x is 3, I've multiplied by b 1, 2, 3 times. So I multiplied by b to get from b squared to b cubed. And I multiply from b again to get from b cubed to b to the 4th. So when that b is larger than 1, I'm multiplying by a number larger than 1. So my y is getting bigger and bigger and bigger. And it gets bigger by more and more each time, right? Because I'm multiplying as I go out. So the end behavior of a growth function is as x goes to infinity, y goes to infinity. And as x goes to negative infinity, y goes to 0. And this is a characteristic of both growth and decay functions. They both have a horizontal asymptote at y equals 0. Okay? Because as I go left, so if I go right, I'm multiplying by b. If I go left, I'm dividing by b. Right? And when I divide, I'll never actually get to 0. I'll just have a smaller and smaller and smaller fraction of the numbers I'm dealing with. Okay? Now, a decay function is if our b value is between 0 and 1, so it's a fraction. So as my x gets larger, the exponent gets larger, I'm multiplying again and again and again by a fraction. Okay? So when I multiply by a fraction, my number gets smaller and smaller and smaller and smaller. And again, I have a horizontal asymptote of y equals 0, because I'll never get to 0. I'll just approach it as I multiply by a fraction again and again and again and again. Now, but as I go left, as x goes to negative infinity, to undo that multiplication, I'm dividing by that same b. I'm dividing by that fraction, so my number gets larger and larger and larger and larger. So the end behavior is as x goes to infinity, y goes to 0. And as x goes to negative infinity, y goes to infinity. But again, both of these have an asymptote at y equals 0. That will be important in a moment as we look at transformations. Okay? Our basic form of an exponential function is y equals b to the x. And if b is greater than 1, it's growth. If b is less than 1, it's decay. All right? Now we'll look at kind of some more complicated forms, as we apply transformations, we'll throw in an a, h, and k and see how those things affect the function. So our general form then of a transformed exponential function is y equals a b to the x minus h plus k. Okay? So these are familiar letters that help us to understand transformations, and they're doing the same things they've done in the other functions we've looked at, right? So again, so this right here is what gives our function its shape, the b to some expression of x. And so that's, I like to say, that's where the magic happens, right? We put the input in, we get an output out of that portion. Once we've gotten the output out, the y, we can multiply it by a, and that'll stretch it or compress it if a is small. Like if a is a fraction, it'll compress it. If a is large, it'll stretch it because it'll increase the height of that y. And then we have k, where we just slide the whole thing up. And this is where understanding that exponential growth and decay functions have an asymptote at y equals 0 is important, because that asymptote at y equals 0 will be affected by the k. So if k is positive 5, the asymptote would be 5. If k is negative 3, the asymptote would be negative 3, right? Okay, so let's look at an example. On page 640, number 6, we're going to do an example there. So page 640, number 6, okay, it says to write the exponential function that will produce the given graph using the specified value of b. Okay, so, and this is, they are always telling you the b because obviously, or that's a key characteristic that you would have to know if you're going to look at a graph and write the function, okay? Because we could map a lot of things to a graph, but here we want to, they have to give us the b to know kind of what our starting conditions are. So here we have b equals 2, okay? So we're going to look at the graph on page 640. And you can see it's keeping that characteristic of going up and to the right. So it is it's an exponential growth function. We're in the lesson that deals with exponential growth functions, so we know that it's kind of keeping that characteristic. And this is something that's come up in previous sections. You'll notice the book typically gives you reference points that correspond to, like, this is the first reference point. And we know what the first point should correspond to, so we draw our a, h, and k out of that. So for instance, a typical function of the form, if we just had y equals b to the x, okay, then your first ordered pairs would be 0, sorry, not b to the x, 2 to the x. We just have y equals 2 to the x because b is 2. Your first point would be, plug in a 0 here, anything to the 0 power is 1, so it'd be 0, 1. Then you'd have 1, 2, because 2 raised to the first power is 2. Then you'd have 2, 4, because 2 squared is 4. Then you'd have 3, 8, and so on. Okay? So those are our reference points. So when they have a first reference point in a graph, they're assuming you know it corresponds to this first reference point. And then the second reference point goes to this second reference point. So that's how we're going to figure some things out. But first, let's look at where the asymptote is, right? So we have b equals 2. We need a, h, and k to be able to write our function. So but that asymptote dropped down from 0 to negative 5/2. So we know that there was a vertical slide down 5/2. So that means k equals negative 5/2. All right? So now we have our b, we have our k, we still need h, and we need a. Okay? So this is where we look at the first reference point, and the first reference point is negative 3, 1 times 2 to the x minus h minus 5/2. So that's the information we have so far. So notice that as we've dealt with before, h is the horizontal slide. So it affects our x coordinate. So if you look here, we went from 0 to 3, positive 3, 1. Okay? We went from 0 to 3, 1. So that means h is 3. Okay? So again, we look at that first reference point. We look at what the first reference point is on our original function if we just had b equals 2. And we see that we went from x equals 0 to x equals 3. So we know h is 3. Okay? Now, we also know that, notice when x is 3, we plug in 3 here, this exponent becomes 0, right? And, I'm sorry, so it is 3, negative 1. I flipped the negative positive when I wrote this originally. So 3, negative 1. Okay? So when we plug in 3 for x, this exponent becomes 0. Anything to the 0 power is 1. So what happens when we plug in this 3 is we end up with a plus k, which is minus 5 halves. So we know that when we plug in 3 for x, we get a minus 5 halves equals negative 1. Okay? So that's how we're going to find our a. We're going to take that first reference point, and we're going to say a minus 5 halves equals negative 1. Okay? Because that's a plus k equals a minus 5 halves equals negative 1. And so that reference point that corresponds to your original x equals 0 point, okay, the y value on that reference point is a plus k. Because in this form, if we plug in, if we get this exponent to be 0, all that's left, this becomes 1, all that's left is a plus k. All right? So now we're finding our a here. So I'm going to add 5 halves to both sides. I'm adding 5 halves to negative 2 halves, so a equals positive 3 halves. All right? So now I have my a, my k, my b, and my h is 3. Okay? So now I can write my function. I can say y equals 3 halves 2 to the x minus 3 minus 5 halves. Okay? And you can verify that that's true by plugging in the second reference point they give you, which is 4 1/2. And you can make sure that it's actually on this graph. Okay? So that's how we would write that function. And again, if you wanted to graph it the other direction, you can start plugging in your first few values. You can map out where your asymptote is using the k. And you can put in your first few values and then know that you're sketching a curve. Okay? So now we're going to look at how to evaluate an exponential function using the graphing calculator. Okay? So now I'm going to jump to 13.2 to show you a decay function. So both of these are the growth and decay functions are the same work. It's just that b is either greater than 1 or between 0 and 1. Okay? So now I'm jumping to page 660 in your book, page 660. And we're going to look at the example number 9 at the top of page 660. Okay? So when we're talking about exponential growth and decay, again, we have y equals a times b to the x minus h plus k, right? So when we're talking about a certain value increasing or decreasing, okay, that starting value is a. Because exponential growth or decay takes place over time, all right, that time becomes our input, all right? And so we're saying, okay, here's our rate of change taken to the power of a certain amount of time. We're going to take that rate of change and we're going to multiply it by our starting value. Okay? So let's look at, and really in this case, we won't use the K as we're talking about what we're talking about now. So they say on a federal income tax return, self-employed people can depreciate the value of business equipment. Suppose a computer valued at $2,765 depreciates at a rate of 30% per year. Use a graphing calculator to determine the number of years it will take for the computer's value to reach $350. So the first thing we have to do is write this equation. All right? So think about what's happening here. A computer's value is $2,765. In the next year, it goes down by 30%, right? So if it goes down by 30%, what am I going to multiply by to get the second year's value? Right, if you said 0.7 or 70%, you're correct. Because what's happening is I have 100% of the value, I subtract 30% of the value, 70% of the value is left. So to get from the beginning value to the value at the end of the first year, I multiply by 0.7 or 70%. And then I have a new value. To get to the next year, I'm going to multiply by 70% again. And it's going to be 70%. In the third year, 70% of the value was in the second year, right? So that's what I'm working with. So I'm going to, so because of this, when we're dealing specifically with models for actual quantities, our B becomes 1 plus or minus R, plus or minus depending on if it's growth or decay. All right? So in this case, it's decay. So I would say my value as a function of time equals the initial value times 1 minus the rate that it changes at. So again, it's going down by 30%, so I'm starting at the whole value minus the amount that it changes by. I'm going to raise that to the number of years, the period of time over which I'm doing my projection. Okay? So in this case, I have V of t equals 2,765. Okay? That's the initial value times 1 minus 0.3 because it goes down by 0.3 each year. And I'm going to raise that to the t power, t in years, because I'm multiplying by 1 minus 0.3 each year. Okay? So to simplify, this ends up being 2765 times 0.7 to the t. All right? So that function will map the depreciation of the computer's value. Okay? So, and there are a couple more examples like this in the lesson. So if you want to go back and see a couple of them written out, you can see them in 13.1 and 13.2. Okay? So, but let me show you how you would graph this, because the question is, determine the number of years it will take for the computer's value to reach 350. So here's how we're going to do that. All right, I'm going to turn my calculator on. I'm going to go to y equals. In y equals, you're going to type in that function, 2,765 times 0.7 to the x. And then we want to find when that function will reach 350. So we also graph the line y equals 350. Okay? Because what we're going to do is find when those two lines, the curve and the line, intersect. Okay? When that curve reaches the 350. So notice, though, that at x equals 0, when x equals 0, this is going to turn into 1, and I'm going to be left with 2,765. So my y-intercept is going to be 2,765. And so I need to make sure that the window of my graph, all right, is accommodates that. So imagine, I believe the default on these calculators is like -10 to 10, okay? So I'm over here, my y equals. I want to set the window for my graph, so I hit the window key. And let's say that yours is set at negative 10 to 10 for the x min and x max, and negative 10 to 10 for the y min and y max. All right, well, I don't need to go 10 left of x because my function starts at time equals 0, x equals 0. So I'm going to change my x min to negative 5 just so I have a little bit of room to the left of the y-axis. All right, and then my x max is 10, and that would mean we're going 10 years into the future. I think that's a good place to start. If we need to look any further into the future, we can change that window later. And then my x min, I'm going to make it 0 because I'm trying to go down to when y equals, or sorry, my y min, I'm trying to go down to when y equals 350. So having the floor of the picture I'm looking at be 0 should be plenty of room. Okay, so I'm going to put 0 there. And then on y max, remember we said that the y-intercept is 2,765. So that's very high. And we want to make sure that we can see that y-intercept on the graph. Okay, so I'm going to change my y max to 2,800, a little bit higher than my y-intercept. All right, so now I'm going to go look at my graph. Cool, so you'll see first it'll graph y1, what we put in y1, which is the curve, and then it'll graph y2, which is where we put y equals 350. So this is the graph of the value of that computer over time, the curve is. This is at time 0, and it's, remember the scale here is from 0 to 2,800, and the scale here is from 0 to 10. So we're getting kind of a warped view of the curve, but where you warped it on purpose for the values that we're looking for. So we want to find out when this curve equals 350, when the y value equals 350. So we want to find out when those two intersect. So I'm going to go to the calc menu. Calc is over here above trace. So I'm going to go second, calc. I'm going to go down to intersect and hit enter. It asks first curve, so it wants me to tell it which two curves I want to find the intersection of. So first curve is that one, second curve is that one. Sure enough, now it wants me to guess where the intersection is, so I move that cursor over somewhere close to where the intersection is, and I hit enter. Now it's working, and it says intersection at 5.7948078. When x equals 5.79 and y equals 350. So now I know that that the value will reach 350 between 5 and 6 years. So in that 6th year, the value of that computer is going to drop below 350, right? At about 5 3/4 years, it's going to reach the value of 350. So that's how you do finding when a curve reaches a particular value using a calculator. Okay, so take some time. Once you've got these notes down, again, you can look back in the lesson or use your online resources from the book to learn anything else or investigate anything else that maybe wasn't completely clear, and then attempt the exercises for 13.1 and 13.2. All right, happy mathing.